What is up, everybody? Welcome to the 13th lecture. Today we're going to be talking about normal distribution. Start off with, what does it mean for something to be normally distributed? What is a bell curve, etc., etc., etc.? Well, up until this point, the book has kind of alluded to what we might be talking about when talking about normal distribution. Every time it's shown you a histogram that if you folded it in half, both sides would be a mirror. That's normally distributed data. And as we add more and more data, as we take more and more measurements, we'll find that those histograms get closer and closer to the bell curve, which is what I've got behind me. And in the case that we could take infinite amount of data, it would look exactly like the bell curve. So what does the bell curve tell us? Well, the bell curve is a way of relating things like z-scores, percentiles, and standard deviations. To start off with, let's start by talking about standard deviations. If we were to add one standard deviation from the middle, so go one standard deviation to the right or to the left, we would find that 68% of our data sits inside of here. Now, what does that mean? Well, that means if our x-axis is our data values and our y-axis is the frequency, well, adding up all of those frequencies will tell you how many data points sits inside of that, right? And in that way, 68% of all the data points we're going to take will sit within this first quartile. Within the second quartile, we're going to have 95%. And within the third quartile, we're going to have 99.7%. All right, well, what about just each of these individual slivers? Well, really all we're going to be doing is subtracting out whatever we need out, right? So if this is 68% of our data, all of this, half of that, subtract half, is going to be just half of that quartile, right? So 34% of our data sits in just side of this sliver. 13.5 would be in this sliver, and 2.35 would be in this sliver. So, noting on these are just some general facts about the bell curve thus far. There's something else I should point out. It may not always be the case that our data is symmetric, and normally distributed and symmetric, like what we have here. We can have what's called a skew distributed, or a skew right, skew left distribution. So, skew right looks like somebody pinched our bell curve and pulled one end to the right. Skew left looks like we did the exact opposite. We pinched one end and pulled it to the left. Having said that, we could look at the data and tell, we could look at mean, median, mode. We should be able to tell if our data is symmetric or skewed. And the way we would do that is by comparing the mean, median, mode, obviously, right, if I'm going to talk about those. In the case that it's symmetric, they're going to be really close. They're going to be arbitrarily close to each other, all three of those values. In the case that our graph is skew right, we're going to notice that the median is to the left of the mean. In the case that it's skewed left, we're going to notice that the median is to the right of the mean. So what does this mean? Well, what this means is that the median, in the case that it's skewed right, is smaller than the mean. In the case that it's skewed left, the median is going to be larger than the mean. Similarly, we could look at the mode. The mode in the case of skew right is going to be less than the median. And the mode, in the case of skew left, is going to be greater than the median. So these are just some ways to look at your data and determine whether or not your data is skewed left, skewed right, or symmetric. Cool, so let's move on. Before we move on to the z-scores, I want to first really quickly talk about quartiles and percentiles. Really all a quartile and a percentile is, it's another way of breaking up our distribution. In the case of a quartile, we would say this is the first quartile if 25% of our data fits in this portion of it, lies under this portion of the graph. We would say this is the second quartile if 50% of our data lies to the left of this. We would say this is the third quartile if 75% of our data lies to the left. Now you might be noticing that quartile, 25%, right? So the first quartile makes sense that it would be 25% of the data is to the left. The second quartile, 2 times 25, 50%, makes sense that we would be saying 50% of the data lies to the left. Third quartile, same thing. Having said that, that also brings us into percentiles. Percentiles are the exact same thing. When I say we're at a certain percentile of our distribution, so this falls within the 25th percentile, it means there's 25% of the data lies to the left. If I say we're at 33rd percentile, that means 33% of the data lies to the left of that line. So forth and so on. Cool. Let's move on to z-scores. Coming back now to the idea of a z-score. All it really is taking a whole bunch of information and putting it together in a nice compact form. In particular, it takes a particular data point, so perhaps it might be a particular height or a number of shoes or number of people watching a TV show at a certain time. It could be 1,000 different things, right? Like whatever our data is about. It could be one particular case of that. Minus the mean, whatever the mean is, and divided by the standard deviation. And oftentimes it's convenient to write this in symbolic form, so we'll just write x minus the mean, x bar, divided by s, our standard deviation, is equal to z. And all this really does is it takes everything we know about normal distribution, compactifies it, and puts it in a nice little package for us and says, here you go. Use this to find other things about this. So, as an example, let's imagine we've got data about the height of men. The average height of a man is about 70 inches. And the standard deviation is about 4 inches. So let's say I told you that there was a particular data point that I was interested in, and it had a z-score of 2.5. I should be able to find out what that data point is. That data point, in this case, is going to be found by rearranging our formula for the z-score and then plugging the values in accordingly. So we're solving for x. First thing we're going to want to do is multiply both sides by s. So s times z. Now we're going to want to add our mean to both sides. And from here, it's just a matter of plug and chug. That's really all there is to this. Now we can do the same thing with another data set. Could be told that we're interested in something with a z-score of 1.6, and that the data has a mean value of 65, and that the data point in particular is 72, and we want to know what the standard deviation is for the entire data set. So we can go through and solve for s. In this case, multiply both sides by s and divide both sides by z. So x minus x bar divided by z is equal to s. And then we just plug and chug. That's really the whole idea of the z-score. That's what it's doing for us. It's compactifying all this information into a nice little package and saying, here you go. Use this instead of having to go back to these graphs every time. At this point, it's only natural to wonder, is there a relationship between the z-score and percentiles? And yes, there is, absolutely. Conveniently, there's a table for it in your book. I'm not going to draw it on the board because there's like 80 some odd values in that table. But there is an immediate relationship between the two. To give you an example, something with a z-score of, let's say, well, let's say something with a z-score of 0.25. It will be in the 59th.87 percentile. So, that z-score should be somewhere right around here, right? Because this is the first standard deviation in both directions, right? So that's 68% of the data. We know this is the 50th quartile at this center point. So, z-score of 0.25 should be somewhere right around here. So there is a relationship here. Moreover, we might be asking ourselves, okay, what if I am given two different z-scores, a z-score, and I want to know what percent of data falls to the left, to the right, or inside of? So, if we're given a z-score, we want to know how much data lies to the left. Well, then we just use that table and we say, cool. Whatever the percentile is, that's the percentile. Done. But what about if we want to know how much data lay to the right of it? Well, then we would find out what percentile it is and subtract that from 100. So we would say, all right, this is in the 38th percentile. So that must mean there's 62% of the data to the right of that. And to find out, for example, a collection in the middle, so we have the z-score to the left and the z-score to the right, well, we would say, what's the percentile here? Now subtract the percentile here from this. And then that'll tell us how much data sits inside of here. Having said that, I know that this can be confusing. So please shoot me an email if you have any questions about this, because yeah, this can definitely be confusing, and I can see how. Having said that, I will let y'all go. Have a good one, guys.